Let us.
Yes, sir. There are 30 participants now, so
Yeah,
I
yeah,
guess
yeah, yeah.
yes, sir.
Okay. Thank you, Dr. Haldar. So let us start today's class. It will be a continuation of what we were discussing in the previous class, and I already have shared one draft. Although note that it is not complete and it may contain a few incorrect slide, but uh, it more or less covers what I taught you in the last class, and I'm going to talk about today. But it is not yet finalized. Maybe after finalizing the whole slide, I'll share with all of you in the common group later, maybe. Okay. And also, I have shared three data sets. I hope all of you have already downloaded those data sets in your system, because we'll be using that data set to demonstrate time series analysis using Jamovi today. Okay. Uh, So I hope I'm clearly audible, right?
Yes, sir.
Okay, okay. Okay, so let us go to the shared screen. Is the screen moving?
Yes, sir.
Yes, sir.
Okay,
Yes.
okay. Okay, so let me then begin. Uh, so we have already seen a few graphs of time series in the last class, and then we have discussed about what are the basic objectives of time series analysis. Like any kind of statistical data, the time series analysis always begin with the exploratory study. So we explore the time series data and report some summary measures. Although we have seen that the summary measures associated with time series data is not same as the summary measure that we commonly encounter, like the mean, standard deviation, and other thing, correlation coefficient. It's slightly different. Then the other objective of time series model is that after carrying out the exploratory analysis of time series data, we propose certain probabilistic model for time series data, and using those probabilistic model, we carry out inferential statistics for time series data. So in this regard, we can perform estimation, we can perform hypothesis testing, and also we interpret the result. Then the third objective and the most important objective of any kind of time series analysis is to predict the future. And finally, there is also another objective of time series analysis, which is called the control. Uh, but we are not going to talk about that. So it is to study a time series to assess what would be its future output value. And then based on that future output value, how to calibrate today's position. So this is called a control problem in the time series context, and mainly engineers, control engineers, they study this kind of problems in the time context of time series analysis, and these also have a lot of applications, but in our course this is not the focus. Okay. Then we have talked about the basic summary measures of time series, and we have seen that essentially there is a summary measure. All these summary measures are functional summary measures, so that means it's not a single number, but it is a function. So if I give you a time series data, out of that, you don't calculate single numbers, but you calculate a whole function of time. And that function of time is one such function is the train function. And we have seen how to calculate the train function. Then other function is the seasonal component. And then the, uh, the whatever left after we remove the trend and seasonality part from the time series data can be regarded as irregular component. Now, we have seen different methods of determining trend. We have seen two different methods of determining trend, and both has certain advantages and certain disadvantages. We have talked about that. At this point, note that we have mentioned one thing clearly, and now I have added that in the slide, that in this talk, we are actually talking about equispaced time series data. So some of this method may be translated to non-equispaced time series data, although, but not all of them, like the notion of autocovariance and their formula. Those formulas are not applicable if we are dealing with non-equispaced time series data, or the moving average method. These may not be directly applicable if we are dealing with non-equispaced time series data. So their theory will be something a little bit different than the usual kind of time series analysis. But however, most often we come across time series analysis which are regularly spaced, which are observed at regular intervals. So the method that we are going to learn, they are applicable more or less all the time series that you will come across. So after we feed the time series data, the trend to the time series data, we can plot the trend separately, and we can also remove the trend from the time series data, and that way it will give us the residuals. And these residuals, how to remove the trend? There are two different possibilities. Like, we have to assume something here. We have to make some kind of structural assumption. And one such structural assumption is that our time series uh, uh, is formed by the trend seasonality and the irregular component in an additive style. So such a model is called additive model under the classical decomposition. This is a classical decomposition. There are many other kind of decomposition of time series. So that's why, but this is the most popular and most well-known and the oldest kind of decomposition of time series, and which is also heavily used. This is called the classical decomposition, and under the classical decomposition, this is called the additive model. And in that case, if you have to remove the trend, you'll just subtract the trend from the time series data, and that will give you the seasonality part plus the irregular component. Yeah. So after detrending the time series, you will get something like this. On the other hand, if you are assuming a multiplicative time series model, if your structural assumption is that the time series data is formed out of the trend seasonality and the irregular component in a multiplicative manner, and we know, we have seen such examples, that what are the data sets where you should assume a multiplicative structural model. We have discussed about that. It is essentially when you will see that the alternating behavior of the time series is present, as well as the amplitude of the oscillation is also growing with or changing with time. So that is an indication of the of a multiplicative time series model. Okay. So in that case, just subtracting trend is not going to work. You have to divide by the trend function to the time series data, and that should give you the detrended time series. Now, once you get the detrended time series, it is the part that now contain only the seasonality part and the irregular component. Now, irregular component is the part that is actually that is a byproduct of many other factors. Okay. So if you are looking into time series model, apart from the effect of time, there may be many other effects like weather, policy, human behavior, many things, share markets. So those kind of additional factors, they are included in the time series data through the irregular component. So the irregular component is actually stochastic in nature, and we have to make some probability model assumption for the irregular part. We'll see that later. So after we remove the trend part and we are working with the detrended time series, then it contains the seasonality part as well as it contains the irregular component part. Then the next step, we estimate the seasonality, or we determine the seasonality, and we remove the seasonality part. For example, here we are assuming, we have also discussed about that. So here we are assuming an additive model. So the trend part and so this is the detrended series. Once you get the detrended series and once you determine the seasonality part, then from this detrended series, the seasonality part is just subtracted. On the other hand, if it is a multiplicative model, So the detrended series would be of the form YT divided by TT. And then again you divide by ST to remove the seasonal component. And after the trend and seasonality part both is removed, then we are left with the irregular component. Now this irregular component is what we have just mentioned, that it contains all the influencing factor. So it contains a lot of variabilities from many different sources. And for that, we have to specify some kind of probability model. But before going into that, since we are still not working with modeling part, but still we are just doing exploratory analysis, we are exploring what is going on there or calculating summary measure. We talk about two other summary measure. The first summary measure is the autocorrelation function, sample autocorrelation function. And the second summary measure is the sample partial autocorrelation function. And I have discussed that sample autocorrelation function will give you an impression that how today's data is connected with the not today, but maybe data associated with a particular day is connected with the data of 3 days that appears 3 days later. So that would be given by the autocorrelation of lag 3. So that will be given by the sample autocorrelation of lag 3. On the other hand, the sample autocorrelation of lag 3 that you are observing, that is really not the true correlation between the value observed on particular day and after 3 days, but it is also because of the common variable or common factors which is the variables that lie in between. So somehow if we really want to calculate the actual correlation or actual association between these two values, then we have to partial out the effect of the intermediate variable, just like you calculate partial correlation coefficient in when you work with multivariate data. So we talk about partial correlation, not the usual correlation, because there are other variables that also affect the association between two variables. So in order to identify the true relationship, you have to carve out their effect from the observing variable somehow, and that is called the partialing. That is the technique of partialing their effect. So we are doing the same thing, and that gives us the sample partial autocorrelation coefficient. So we have used two different notation for them. Now the right hand side gives you the sample partial autocorrelation function, and the left hand side gives you the the sample autocorrelation function, and it also has a popular name which is known as correlogram. This is called correlogram. This doesn't have any such name, but this has a standard name in literature. This is called the correlogram or sample autocorrelation coefficient, or SACF. This is the SACF and this is the SPSCF. So these are very important summary measures associated with the irregular component. Now, as I have just mentioned, that this irregular component contains a lot of influencing factor. So in a sense, it is stochastic in nature. So that means I cannot model it just via a deterministic function. Like I cannot say IT is equal to A plus BT, or I cannot say IT is of the form sine T plus 2 cos T, because that would be a completely deterministic object. Okay, I need to specify a probability model for this IT part. So let us specify a probability model. So this would be the modeling part. So once you have done with the exploratory analysis of the time series, then the next step that you will do, you will do the modeling of the time series. You will try to specify an appropriate model, probability model for your data. For the note that we are not searching for a probability model directly for the original time series data. But after removing the effect of trend and seasonality, we are left with this irregular component. And for that irregular component, we are searching for a probability model. Now, once we are able to search for a probability model and specify, perform test and specify probabilistic statement for this irregular component, I can simply add back those trend and seasonality part to get a similar statement for the original data. So that's why we don't specify a probability model for the original data, because that would be more complex, because that not only contain the probabilistic part, but that also contain a complicated seasonality uh, component, that also complicated a maybe that also contain a complicated trend component. So already this part is difficult, some proposing a probability model. So we don't want to make the task more difficult. So that's why we break the task into step-by-step procedure. Like at first step, we take care of the trend part. In the second step, I take care of the seasonality part. And after those are removed, then we take care of the underlying probability model. So this is how we proceed in any kind of time series analysis. So if you have any question, please feel free to stop me and ask. I hope you don't have much question till this. Okay. Now we assume a very basic probability model. Like I assume that this ITs are, I assume a probability model ZT are independent and identically distributed with a bell-shaped curve. And this ZTs would be a model for this IT. Is it clear?
Sir, please repeat.
Yeah. So maybe I can explain it. So in the whiteboard. Okay. Yeah. So I am assuming so what is the meaning of that? Suppose I am assuming this as a probability model for my IT. What is the meaning of that? So let us, before going into that, suppose you have a conventional kind of data, the usual kind of data. Suppose you are measuring uh, something on in patients. Now, generally, when you talk about a probability model for this kind of a data, what you assume? Don't you assume such a model for such kind of data? So suppose these are the measurements taken on in patients, then the background probability model, the basic, very basic probability statement that you make in this context is that x1, x2, xn, IID, normal, mu, sigma square. I'll explain what is the meaning of that. The meaning of that is uh, when you haven't measured the variable for the first patient, yet you measured, you are till to measure the variable for the first patient. You don't know the value, actual value. So there are some uncertainty, but you already have something at the back of your mind. And what you know that somewhat from my experience, I know this value should be around this region mu, maybe this mu. And what you know from your previous experience, maybe previous experience or previous study or previous data sets, that a suitable probability model for this x1 would be such a curve. So basically, it's the usual bell-shaped curve or the normal probability curve. So what we assume that until we measure or until we take the measurement on the first patient, if someone asks me what you expect, what do you expect about the measurement? I'll tell him or her that I'll expect that the measurement will be following some kind of bell-shaped curve like this. And there is a high chance that the measurement will be coming around this mu part. And if that person asks me what is the possibility that the measurement will be coming from this part, this region, I'll say it is very less. Because we know from the bell-shaped curve that within plus minus 3 sigma of mu, almost this is maybe mu plus 3 sigma and mu minus 3 sigma. All the values or all the probabilities will be falling within this region. So that means uh, if I take measurement, finally when I take measurement, it will follow this bell-shaped curve and it will be coming somewhere in between this mu plus minus 3 sigma region. So the possibility that my observed value for that first patient will be coming from this region, that probability is very less. So it is almost negligible. So I can answer such questions, and answering such questions is possible because I'm assuming that this hypothetical number is following some probability distribution. So there is a chance factor, there's a probability factor that it has very high probability that it will lie between this region. It has very low probability that my data will be coming from this region. It has very low probability that my data will be coming from this region. So that I am able to say because I'm assuming a appropriate bell-shaped curve. If I don't assume such a bell-shaped curve, then I cannot make such statement. And how I am making such statement? Based on my previous experience. So the previous experience or previous known theories by other people, developed by other people. So we have some belief that if we are going to measure the height of an individual, that will be following some bell-shaped curve. I'm just saying hypothetically. Okay, so it will follow bell-shaped curve. So after you make the measurement, then you get this x1 number. Now you get a particular value. Now it is not a random variable. But before you make the measurement, if I ask you before making the measurement, this is not a fixed number. Once you have measured, you might get some value like 1.7 meter height of an individual. So after you make the measurement, but before you make the measurement, if I ask you what would be the value of your measurement, then you won't be able to say anything, but you will be able to say that, okay, I believe my value would be centering around 1.6 and it would be according to a bell-shaped curve. And the very high chance that it would be within the range maybe 1.2 to 1.9. Okay, if I'm talking about Indian population, something like that. Okay, so you are going to make such statement before taking the measurement. But once you take the measurement on that particular patient, now you have a definitive value, like you got a definitive value 1.7 meter. Okay. So that is what is a probability model. So before making the measurement, there is a hypothetical object that gives you the probability model, and most often we this is called the random variable. And these random variables are basically a basic hypothetical analog of the data, something like that. Similarly, for the second patient also, once you have observed the first patient, for the second patient, if I am asking you, what do you think? What would be his or her height? Again, you will see, you will say that it will be according to a bell-shaped curve and the same bell-shaped curve. It's not like that you are changing your bell-shaped curve. Okay, so that means the first random variable follows a normal mu sigma square. The second random variable also follows the same normal distribution. I mean, if it is changing, then it is not identical. So that's why these two are identically distributed, because they are following same normal. The first one is following normal mu sigma square, second one is also following normal mu sigma square. Had it been like this, that the first one is following normal mu sigma square and the second one is following normal mu plus 1 comma sigma square, then they are not identical, they are different. But there is no point assuming that one particular patient has something different with the other patient, because we are assuming that we are working on a homogeneous group of patients. If it is like that some of these patients are Indian and some may be coming from European country, then it is not going to work. Then you have to work with different models for each one of them, because they have different kind of height, different heterogeneous group. So for n patients, then I can assume that the background random variables are following normal distribution and they are same distribution, so they are identically distributed. Now the question is that if we talk about the correlation between these two random variables, in a sense, if the height of a particular individual is suppose 1.7, what it tells about the height of the next person? It doesn't absolutely tell anything, because these two people are unrelated people. It doesn't tell you anything about the next people. So that means these two random variables are not connected at all. So if you calculate their correlation, theoretical correlation, since now these are no longer data set, you cannot calculate correlation like a data set, but these are hypothetical objects. There is a similar kind of, but of course slightly different formula for calculating the correlation between the random variables. Okay. And if you calculate the correlation between this random variable, it should give you 0. So in a sense, these are uncorrelated or independent in a sense. So in this case, that's why you can say x1, x2, xn are independent and identically distributed with normal mu sigma square. So that means these are random variables, hypothetical objects, which are all of them are independent of one another. Secondly, all of them are identically distributed, and all of them are distributed like a bell-shaped curve. So that is what I'm suggesting. So this is my basic probability model for such a data. So is this part clear? Can I assume that this part clear to everyone?
Sir, yes, sir.
Okay. Now suppose I am assuming the similar kind of a model assumption for this ZT. So then that means this Z1, Z2, Zn, these are the random variable. I'm assuming Z1, Z2, Zn are IID normal 0 sigma square Z. So previously I was talking about mu sigma square. Now my mu is Z, 0. And in case of sigma square, I'm using just a slightly different notation to make it clear that it is related to this Z. Okay. Then I got an irregular component at time 1. I got an irregular component at time 2. Similarly, I got an irregular component at time n. So that means this is the hypothetical random variable and this is the observed data. This is the hypothetical random variable at the second time point, and this is the corresponding observed data. But see that this cannot be a good model for it, because if you calculate for such a hypothetical model, this Z1, Z2 are uncorrelated. Whereas the irregular component, from the picture of the irregular component, what do I have seen? That if you look into the sample autocorrelation function, it is not 0. The autocorrelation at lag 1 is not 0. So that means that the irregular component of today is not independent of irregular component of yesterday. So definitely there is some correlation. On the other hand, the background hypothetical random variable, they doesn't have any correlation, because you are assuming this particular model. Okay. So that is the problem. The model you are assuming and the data you are working with, they have different kind of correlation. Your model is telling you that if I calculate correlation between today's data and tomorrow's data, they will be 0. If I calculate the correlation between today's data and day after tomorrow's data, that will again be 0. So that means it is telling you for every lag, the correlation is 0. The model you are assuming. On the other hand, your data is showing, no, for every lag, the correlation is not 0. Maybe up to lag 12, the correlation is there, and after that, it is. It is not going to be a good model for the data at hand. Is that okay? Is it clear to all of you? So then I will go back to the slide part and explain from there.
Sir, in real terms, what can we infer from this, sir? If, for example, if let's say we have 10 cancer patients, and
Right.
we have seen that let's say they are having carcinoma breast, sir, and uh, the historical data says that all of them have a survival probability of only 2 years. And then we take the next cohort of 10 patients and we then predict how much they will survive. Can you, sir,
Right.
explain this with this example, sir? Am I giving the right example, sir? Am I?
No, actually, that has nothing to do with time series.
Okay, okay, sir. Sorry, sir.
Yeah, that is more like the example that associated with the conventional kind of data where you see identical kind of observations and they may not have any correlation. But in the context of time series data, what I am saying that my data is showing that there is correlation from the sample autocorrelation function. On the other hand, the model I am assuming, the model is telling me there is no correlation. So can that model be a appropriate model for my data? Because what I'm observing in the data and what my model is telling, they're not matching. So definitely that model cannot be a good model for the data. So that is what I'm trying to say.
Okay, sir. Okay, sir. Thank you, sir.
Okay. Okay. So so that means if I take this to be the model, it is not going to work. I'll show you this part later. Then I directly go to the picture. Now here I try to motivate the same thing. If xt is a good model for the irregular component, so the model is like, as I have explained, that model is like a ideal object. It's like a theoretical object. It's a random variable. People can do mathematics with this ideal object. Now, if this ideal object matches well with what you see in reality, which is the irregular component, which is the real life data, which is empirical, which is tangible, you can measure, you can get the value. On the other hand, this xt, which is like the hypothetical, that is not something that you can measure. Okay, but it's a mathematical model, or it's a mathematical equation, I may say. So it is a mathematical equation for this real life data. Now, if this mathematical model is good enough for the real life data that you are observing, then the autocovariance function or the covariance between the hypothetical objects. So since these are random variable, as I have told you that you can calculate the autocovariance function. Sorry, I think I have made a mistake here. It should be autocorrelation. It's not sample or auto covariance. Okay, so and it is not covariance, it's actually a correlation. So there are typos maybe in the slides. Okay, so then if you calculate the autocorrelation function for the hypothetical object, and you know you already have a autocorrelation function for the real life data, because that is what we refer to as the sample autocorrelation function. So these two should match, right? These two should match. Now here, can you see the picture? So can you see that this green color line, that gives you the sample autocorrelation function for the irregular component. On the other hand, this red part, this red line is giving you the theoretical autocorrelation function for the hypothetical object. For the hypothetical object, which is the x. And you see the hypothetical object has an autocorrelation function which only have a spike at the zeroth lag and doesn't have anything else, because that is what is expected, because I have assumed a very simplistic model, like they are identically distributed and independent. So there is no relation between two consecutive time point, the hypothetical object of two consecutive time point, and that cannot be a good model for the data. Okay, because the red part and the green part is not at all matching. If it is a good representative of the data, then the population version or the ideal version or the theoretical version, which is the xt, its mathematical function should at least look similar to what you are observing in the real life data. It definitely won't be exactly same. That is not possible. Anything that is mathematical and anything that you are observing in reality, they cannot match exactly, but If there is a close approximation or at least some kind of parity between them, then we are happy. But you can see that that is not at all matching. So this model that I have talked about previously, so this model has a name. This is called the white noise model or white noise process. Now this, as it is evident from this picture, that white noise model is not a good model for the irregular component. Okay. Now white noise is not realistic. So suppose these ZTs are IID and I'm just trying to use this ZT as a model for this IT, then it is not going to work, as we can see from the picture. Now comes the question, can I take a mixture of this ZT? Like I take one particular ZT and previous ZT and multiply with theta, and I create something like this. Instead of directly working with the ZT, previously I was directly trying to model this irregular component with the ZT. Now what I do, I just take some kind of combination of ZTs. And I'm saying that after taking the combination of ZT, I'm getting something. This something now is a good model for the IT. That is what I'm suggesting. Now, such a model is called moving average process. Now, I think one of our participant was asking about moving average in our last lecture. So that time when he was talking about the moving average, it is this moving average. Now we have also talked about another kind of moving average. Like if I go back in the slides. So we have studied a moving average method for trend determination. A moving average process and moving average method for trend determination, these are completely different objects. Like this moving average method for trend determination, this falls under the exploratory analysis of time series. On the other hand, this moving average process, this falls under the category of time series model. This is actually one kind of time series model. Okay. Now, since we are just now taking the combination of ZT and the ZT that was observed in the previous day. Now, what is this theta? This theta is some number. So I'm taking some kind of a combination of this ZT. Like I may take theta to be 0.5. Okay. So I'm taking combination, or I may take theta equal to 1. So that means I'm taking the combination and I'm giving equal weightage to ZT, today's error and the yesterday's error. So this ZT is often called the error process. Okay. So I'm giving equal weightage to them. And that way I'm forming the model. So this is called a moving average process. And actually this is called a moving average process of order 1. Why order 1? Because only one theta is there. This concept can be readily generalized to moving average model of order Q. For XT is, just recall what we have done. We have taken a ZT IID normal 0 sigma square Z and try to tell you that this ZT may be a probability model for this IT. But we have seen from the picture that the covariance function of this ZT and the parallelogram of this irregular component, they are not at all matching. Okay, so they are not at all matching. So what we have done, instead of working with this ZT, we have taken this ZT plus maybe 0.5 ZT minus 1, and I call that this may be the appropriate model for this irregular component. But that idea can be extended. Why not ZT plus 0.5 ZT minus 1 plus 0.3 ZT minus 2? So that means I am taking a more rich kind of combination. So here I was taking combination of only two errors. What if I give the flexibility that I can take combination of so many error part? So definitely that would give me a richer kind of probability model for the data. So this sort of a model is called MAQ process or MAQ model. I'll show you. So these are just mathematical equations. Okay, you don't have to bother too much about this thing. Why this is called MAQ? Because in MA1 you have only one parameter. You have in MAQ you have Q parameter. So this will be another probability model. We hope, at least we hope so. Is it okay?
Sir, what is theta here?
This thetas are the parameters. These are like parameters. So this you have to estimate from the data. So once you fix the value of this theta, then that will give me a particular MA. Now, a particular MA may not be matching well with my observed data. So that means I have to apply some kind of statistical technique to find the suitable value of theta so that this MA1 is matching very well with the observed data. So let me explain by a picture. So you have already seen that white noise is really not a good model for our data. So now my question is that, can I work with a MA model, MA1 model? And is MA1 model a good model for the data? So recall that this is the equation of MA1. So let us see. This is definitely one such process like white noise, and it must have some kind of theoretical covariance function. We'll just try to match whether the theoretical autocovariance function and the correlogram, they are matching or not. For white noise, they are not matching. It is clear from the picture. So let us see whether the MA it is matching or not. Can you see that now there are two red spikes? In white noise, there was only one red spike. So that means this is actually this red one is the lag 0. So lag 0 means basically you are calculating the correlation of today with today. So that will definitely be 1. So perfectly correlated. Today's data is perfectly correlated with today's data. That is actually not giving you anything new. But we are actually in time series analysis, we are interested that how far today's data is connected with tomorrow's data. So that means we are actually interested in lag 1, or we are interested in asking question that how today's data is connected with day after tomorrow's data. So in that case, we are looking into the correlation of lag 2 like that. Okay. Now,
Can I have a question?
yeah, sure.
Sir, in theoretical models, we just studied about that there is no correlations between the values. Means there is no correlation between the lag 1, lag 2, lag 3, lag 4, like this.
Right.
But here, then it should be in the first figure. Then it should all should be in the within that two lines. Means the no correlation lines.
Right.
Why this is in the positive and some are in the negative directions.
Right. So that's why it is not matching. So the theoretical model, the autocorrelation of the theoretical model is given by the red line, and the autocorrelation for the real life data is given by the green lines. Now the red line is telling you that we are working with a model which doesn't have any correlation for lag 1, lag 2, lag 3. So that's why you cannot see anything, any red spike. But the real life data is telling you that there is autocorrelation. So that's why I am suggesting that this white noise is not at all a good model for this the real life data. So is it answering your question?
Yes, sir. Sir, what about the second picture?
This is actually the partial autocorrelation function. This is also not matching. You can see that there
Here
is
the red line is not there. That's why.
right. So there is no red line is there. Actually, we are not, for the time being, I'm not talking about the second picture. I'll be only talking about the first picture, at least initial for initial few models, and then I'll talk about the second picture.
Okay, sir.
Okay. Now let us see. This is an MA1 model. Now this is an MA1 model where I have taken maybe theta equal to 0.5. Now if I could have taken theta equal to 0.7, then maybe it increased little bit. Or if I take theta equal to 0.2, maybe it could have decreased little bit. So that means for different values of theta, I am getting different processes. And theta is like an parameter. So what I'll do, I'll choose this value of theta based on the observed data. So which will give me the kind of the best possible MA process. of order 1, which aligns best with the observed data. That is the and that will give us the statistical inference. So that is the objective of statistical inference. We start with, like, when I say that my data is coming from normal mu sigma square model, I really don't know what is the particular value of mu and sigma. So what I do, I try out different values of mu and sigma square. And for some particular values of mu and sigma square combination, I'll see that that bell-shaped curve matches very well with my histogram. If I plot the histogram of my observed data, some particular combination of mu sigma square will be there for which it will match well. So that will be the value of the unknown parameter mu sigma square. Similarly, here also for some particular value of theta, that rate spike perhaps should overlap with the green part, and then that would give a better matching with our observed data. So this theta is like the parameter. So it tells us that how much strength or how much correlation is there in lag 1. So this is what theta is telling us. So Dr. Dey, I hope I answered this question.
Yes, sir. Thank you so much.
Okay. Yeah. So these are like the parameters. So basically, the whole objective of time series modeling is that to use some kind of statistical technique to estimate this parameter. Just like when we deal with normal mu sigma square, our objective is to apply some statistical method to estimate the mu and sigma square. Here also the objective, ultimate objective that will show that is to estimate this unknown parameter theta. Now this is when we are considering MA1. Now if I consider MAQ model, this is of course a more flexible model, but that comes with the additional burden that now I have Q parameters. Theta 1 is an unknown parameter, theta 2 is an unknown parameter, theta Q is an unknown parameter. So I have to estimate Q many unknown parameters from the data using some kind of statistical technique, and that is the sole objective of time series model. Now we have again go back to that picture. Let us see that white noise is not really a good model for this irregular component. Is MA1 a good model for the irregular component? No. Because what is happening with the MA1? You can see that at lag 0, it is 1. Lag 0, it will always be 1, because lag 0 means you are correlating or you are calculating correlation of today with today. There is no gap. Lag 0 means there is no gap. So it will be perfectly correlated. So correlated will always be +1. So here
Sir,
at
can you
lag,
please use the pointer so that it will be easy for us to look at?
okay. Pointers.
At least cursor.
Yeah, maybe I think I can use a line, maybe a pencil, maybe as a tool. Okay, so here you can see that the red in the lag, this is lag 1. In lag 1, you can see that the red spike goes up to this length. So the green spike is there, but after lag 1, there is no red line. On the other hand, the irregular component in your data is showing, no, my correlation doesn't go away after lag 2, but it remains maybe after what, lag 12, 13, like that. So that means MA1 is also not a good model for the data. Is this part making sense to everyone? That MA1 is really not a good model for this data?
The first one is the lag 0.
Lag 0. So in lag 0, the green and the red are completely overlapping, because in lag 0,
Yes, sir.
both are +1. So that is nothing informative. But you have to
Okay.
start from lag 1. In lag 1, the red has some height. The picture is actually perhaps not visible to you because it's very thin, this line. So you can see that this
Okay, sir.
from there, this is the red line, and this is not completely overlapping with the green line, but still there are some similarity. But the problem is that when you go to lag 2, there is no red line. So that means your theoretical model is telling you that, okay, after day 2 onwards, there is no effect. On the other hand, your data is telling, no, wait, I have effect till day 13. So how can this be a good model for the data? So MA1 is also not a good model. The model that I have shown you, it's not good for the data. Is it okay?
So there is some correlation in lag 5, sir.
Yeah. Correlation in lag 5, lag 6, lag 7, everywhere. On the other hand, the model you are considering, it is telling you that after lag, this is lag 0 and lag 1, and then for the other part, there is no correlation. It become absolutely 0. So this cannot match with the data. Do you
Sir, I
agree with?
think lag 5 is matching with the irregular component.
No. How? There is no rate spike. It may look like that, but there is no rate spike. This one, right? This one doesn't have any rate spike. It look like that, but there is no rate spike.
Okay.
So this was MA1. What about MA2? So MA2 means, let us go back to this slide. MA2 means I have only ZT plus theta1 ZT minus 1 plus theta2 ZT minus 2. That would be an MA2. Let us see whether MA2 will be a good model for the data. So this will be MA2. Can you see in the MA2 at lag 0 there is a rate spike, at lag 1 there is a rate spike, and at lag 2 also there is a rate spike from here. Can you
Yes.
see that?
Yes,
But
sir.
see that beyond lag 2 there is no spike. So can you observe one thing, that in MA1 only up to lag 1 there was a spike, and in MA2 there is only up to lag 2 there is a spike. So similarly, we can guess that maybe if we work with an MAQ model, then only up to lag Q there will be correlation, but after lag Q there would be no relation at all. So let us see that whether that is true or not. So this is I have shown you an MA5 model. So in MA5, can you see that the theoretical MA5 model has a correlation at lag
Lag 5.
up to lag 5. So this is lag 1, this is lag 2, this is lag 3, this is lag 4, and this is lag 5. In lag 5 also you have a that is insignificant, but still some correlation is there. Anything that falls within this band is called insignificant, but still there is some correlation. That is a very insignificant correlation, but that there is some correlation. So it go up to lag 5. So then from there, I can anticipate one result, that if I am working with an MAQ model, or I'm working with such a model that xt is equal to zt plus theta1 zt minus 1 plus theta q zt minus q, such a MAQ process, then if I calculate the autocovariance function of this MAQ process, what we'll observe that it will go up to lag Q, and at lag Q it will take such a value, and after lag Q there will be no autocorrelation. So this is a typical property of MAQ process. So after Q lag there will be no autocorrelation.
Sir,
Yeah,
so when we are dealing with actual data
yeah,
and when we try to fit in model
yeah,
in practical setting, what we would be looking at is that let's say if today's day zero, which is lag zero,
right,
at how much date we will have the data which will have zero correlation. Is that
right. So
correct, sir?
that means you will be, in reality, you will be looking for where the correlation crosses this line, that lag, something like that.
So the moment it stops crossing is is the is the is the date that we are looking for actually, sir.
Yeah,
Right, sir?
right.
But sir, as per the these two lines, so it is only for a particular period only that our data is having zero correlation, and then it starts going towards the reverse direction.
Right. So this particular data set, it is happening,
Okay, sir.
and that we'll talk about that kind of thing later. So this is basically some kind of seasonal component. So there is some seasonal component, and seasonal effect is there. That's why that is going out in the reverse direction. Had
So
had there been no seasonal effect, this was not. You won't see that. If there is no seasonal effect, you perhaps will see that it will be like this. So that
yes,
means it's the lag where this line will be crossed, and beyond that lag, you can assume that there is no correlation. So
so
something like
sir,
that.
sum-
Yeah,
summarizing, so when we are dealing with actual data set, so
right.
our focus while calculating the summary measure will be to find at which lag the correlation ceases. Is that correct,
Right,
sir?
right.
Sir, we have already defined the seasonal components, sir. And then where can we find that seasonal components?
Right, right, right. So even after removing the seasonal component, there may be some seasonal part remaining. So that's why you must have seen that in this slide, not in the slide, maybe in the we often talk about SARIMA model, like seasonal autoregressive model. So those are the kind of model which dealt with such residual seasonality, that even after removing seasonal components, some seasonal part may be remaining inside the deseasonalized time series, which cannot be removed in such a simple-minded way. So you need to create a model that can accommodate such seasonality, which cannot be removed. So you can think of it in this way, that the seasonality part has two kind of ingredient. One part is that is removable seasonality, and another kind of seasonality which is not removable. Now this is kind of the seasonality which is not removable part. So when you deseasonalize the time series part, you actually remove the removable seasonality part. The remaining, if there is non-removable seasonality in your model, that have to be appropriately modeled. That cannot be removed. So there, that's why we talk about the SARIMA model, the seasonal ARIMA model. The seasonality comes there. Okay. Okay. So so we see that MAQ model may not be very good, because the problem of MAQ model is that if I am working with MA5 model, only after 5 lag, there will be no correlation. Whereas my data, the deseasonalized, detended deseasonalized data may show that I have correlation up to lag, maybe lag 13, 14. So MAQ is not appropriate. So what can be an alternative model? There is another type of model which is called the autoregressive model. Why? You'll see. Sorry, there is some problem with the notation. Yeah. So these are the glitches that I still have in the slides. So maybe I'll share a better slide with you later. Okay. So this xt is phi. This should be xt minus 1. I actually meant this xt minus 1 plus jt. So this kind of a process is called autoregressive process of order 1. So why? So this is something like an equation like this. this kind of an equation. So this kind of an equation we see in regression problems, that you have an independent variable x, you have a dependent variable y, and you are trying to estimate this phi. So that's why this is a regression problem. Here, your equation looks very much like a regression formula. It is just telling you this. And the only difference is that in a regression problem, x is something, an independent variable, and y is something else, which is a dependent variable. But now in this case, there is no question of y, only x is there, only single object is there. Now one is the measurement of that same object yesterday, and this is the measurement of that object today. So that is what is given by this equation. So it looks like a regression equation, but it's really not regression, but it is regressing the dependent variable on itself. Okay, so that's why it's like regression on itself. So that's why the name is autoregression. This is called autoregressive model or autoregression. So this is an autoregressive model of order 1. This concept can readily be generalized to an autoregressive model of order 2, order 3, like that. Oh, okay. First, we'll see what happens with autoregressive model with order 1. So this is an autoregressive model of order 1. Can you see now that this autoregressive model of order 1 has some nice property, that now at least the autocovariance function of this autoregressive model is not suddenly getting chopped off like an MA model. So it has a relatively better behavior, that it is decreasing gradually. So which actually matches well with the data, although not exactly, but still it matches well with the data. So that means AR1 is at least better than MA. It looks like, at least. But still, it is not really a good model. So why it is not a good model? If you look into so far I was just talking about the left picture. Now I'll be talking about the picture on the right panel. If you look, if something is a good model for the data, I was trying to say that if a model is appropriate for the data, then the autocorrelation of the model and the autocorrelation of the data, they should match. But the same thing should be true also for partial autocorrelation. That the autocorrelation, partial autocorrelation for the model and the partial autocorrelation for the data, they should also match. But see that is not happening, because the data has partial autocorrelation maybe after lag 2 it is okay, lag 3, 4, 5, 6. Then at 6 there is a partial autocorrelation which is falling outside the band. Then 7, 8, 9, 10. At 10 also there is a partial autocorrelation outside the band. So what can I do? So actually I can extend the concept of AR equation. So instead of including this kind of a equation, what I can do, I can not only include the data of yesterday, but also the data of day before yesterday. So then that would be a richer model, because I'm using more data from the past, and I'm sort of saying that today's value will not only depend directly on yesterday's value, but it also depend directly on the day before yesterday's value. So of course I'm giving more flexibility. So I can hope that would give me a better model. Let's see what happens in such case. So that will give me a AR2 model. So similarly, I can extend the concept of AR2 model to AR4 model also. And actually, we can show that this is a property of AR4 model, that in AR4 model, the partial autocorrelation go up to lag 4. So this is a property. So, but you can see that AR4 is also not a good model here. So what can be a good model? The problem, so summarizing these findings, I can say one thing in this point, that that if I am working with an MAQ model, the problem of MAQ is that if I work with the autocorrelation sample autocorrelation function, the model autocorrelation function, it will go up to lag Q and then it will become 0. On the other hand, the problem of AR is completely opposite. In AR, the autocorrelation function will behave well, but if you look into the partial autocorrelation function of an ARP model, then the partial autocorrelation will go up to lag P, and then it would become 0. But in reality, what happened when we are dealing with data, we'll see neither the autocorrelation is dying out very quickly, that after some lag it become completely 0. It doesn't happen. It actually decays gradually. Also, for the partial autocorrelation, we'll see that partial autocorrelation also doesn't get chopped after some lag. So it will decay gradually. So that means none of this MAQ or the ARP may be a good model for our data, because they are having, if you are trying to use MAQ, that is having problem in the ACF part, and if you are trying to calculate the ARP, they are having problem in the partial autocorrelation part. So its partial autocorrelation doesn't really matches with the what we observe in the data. Okay, so that is a problem. So what we can do, we can somehow combine this AR and MA together to form something which is called the ARMA model, autoregressive moving average. So what is the idea? The autoregression models are like this. This is on the other hand, this is MA1. Now what I will do, I'll combine the notion, the concept or the formula of AR and the formula of MA together to suppose I give such a formula to create a model. So can you see that this part look like the MA equation, and can you see that this part look like the AR equation? So this is somewhat intermediate or mixture of both AR and MA. So such a process is called an autoregressive moving average process of order 1,1. So why 1,1? Because the AR part, this is the AR part, has only one coefficient. So this is 1, and the MA part also have only one coefficient. So that's why it is MA1. Now suppose in the AR part, I could have included P such coefficient, and the MA part I could have included Q such coefficient, then that would have given me the ARMA PQ process, which is the general ARMA PQ process. ARMA PQ will be a good model for this irregular component. So is it okay?
Yes.
Okay. So this is the ARMA PQ equation. So the why this is ARMA PQ? Because the AR part involved P such parameter, and the MA part involved Q many parameters. So that's why this is called ARMA PQ process. So this is just a mathematical equation for writing a process. But what is more important is seeing how this theoretical object behave, or how their covariance function look like. So I'll show you that their covariance function would look very much like our data. So this is the I have considered an ARMA 5,4 model for the data. How I got this ARMA 5,4, how I have chosen this value to be 5 and this to be 4. That I'm not going to discuss for the time being, but there are statistical method for getting that. But once I have got this MA, the value of P and Q, I can apply statistical method to estimate the unknown parameters of the ARMA PQ model, and I plot their autocovariance function. Can you see that the red color autocovariance function and the green color autocovariance function, which is the related to data, they are actually matching very well. I mean, quite well up to this lag. Now, this has a spike in the opposite direction. That part is not matching, but apart from that, it is matching very well. Similarly, if we look into the partial autocorrelation part, you can see that the green part, which is the reality, which is the empirical data, and the red part, which is our theoretical model, they are also matching very well. So that means ARMA PQ process will be something which will match well with our data, both in terms of the autocorrelation function as well as partial autocorrelation function. So that's why ARMA could be a better model rather than working with AR or MA, because AR and MA has certain limitation. Like I have told you that for AR, after lag P, the partial autocorrelation will die out completely. So that's why they may not be very realistic. On the other hand, for MA, after lag Q, the autocorrelation will die out completely. So that's why they also are not very realistic. But on the other hand, for ARMA, none of the correlation will die out completely. It will decay gradually, but it won't die out suddenly. So that's why ARMA models are more realistic for this. Okay, but still, sometimes it may happen you are working with such a data so that an AR may be a good model. That is a possibility, but ARMA is a more general, more flexible kind of model. And actually, AR is just a special case of ARMA. If you consider an ARMA with 5,0, it will basically give you an AR model of 5.
Sir, where can I find that whether it is 5-4 is a good model, why not it is 4-5?
Right. So there are statistical approaches for doing that. Okay. So basically what you have to do, you have to run some software packages which will automatically choose the order of the model. Actually in Jamovi, the order will be automatically selected. So, but automatic means the software will run some kind of statistical algorithm to get the value of PQ. Something like that. But we'll see that. Okay. So is it all right till that part?
Sir.
Yeah.
Sir, I want to just say that if we are trying to analyze the number of weekly cases at the hospital,
Right.
and the ARMA 5-4 model will help us to understand like how the number of cases from past 5 weeks influence the number of cases in the current week.
Right.
And so that will help us to plan our resources efficiently and manage the situation.
Right. So in a sense, you feed that ARMA model to your data, and you will forecast. I haven't yet talked about that forecasting part. You will forecast, and based on the forecast value, you'll see that what is the expected number of patients in the coming week. If that become very large, then perhaps you have to use some kind of you have to replan your arrangement of managing these patients. And if you see that no, the forecasted value comes within a stipulated interval, and they can be managed in the current setup, then you should retain the same setup that you are currently running. So it would be something like that.
Okay, sir. Thank you.
So it is something like that control problem. So you look into the forecasted value and then calibrate today's position. that whether you have to make some kind of new strategy to incorporate all these patients that will be visiting the hospital in the coming weeks or coming years, or if the current strategy goes well. So it is something like that control problem. But anyway, the idea is you have to do forecasting and check whether the forecasted values are uh, uh, lying in the stipulated interval or not, or whether it is blowing up too much. Okay. So let us then talk about a little bit of ARIMA model. So I'll just write down a few models, and then I'll try to be more interactive in this case, because these are mathematical equations. Sometimes it doesn't look very nice object to work with. So suppose I work with this model. So what is this model? Can any one of you volunteer and tell me? You already have seen this thing.
Sir, MA
Yeah.
of 0.5 order.
MA
0.5 order. Sir,
MA
MA
one
MA1 MA1 model.
value of
You have only one parameter. Okay. Can you tell me what is this model?
It's an ARMA model.
ARMA of
It's
order
around
what?
2. 2 and
ARMA
1.
to 1.
1, 2.
2, 1. Because
Yeah.
this part contain two unknown
Okay.
parameters. I mean, I have put some values
2.
of this unknown parameter, and this part contain only one unknown parameter. This jet is the present noise. So this is ARMA 2, 1. Okay. Now, what happened in reality? What I have told you, that given a data, when you deseasonalized and detrained your data, then you are left with the irregular component, and you try to give a model for the irregular component. Now, what happened? Sometimes an MA model is good enough, although very rarely. Sometimes an AR model is good enough, although again very rarely. And most of the time you will see that an ARMA model is good enough. However, that is not the case all the time. Sometimes it may happen that neither AR nor MA, neither ARMA, none of them are actually working well for the data. Particularly, you'll see in such case of in such kind of data, what would happen? In such kind of data, you'll see that your autocorrelation function actually would grow very slowly. So sometimes these sort of things are evident, that even after doing deseasonalizing, detrending, and doing any kind of many kind of thing, all these operations, your autocorrelation of the irregular component, the autocorrelation function of the irregular component, that would decay very slowly. In that case, neither MA nor AR, neither ARMA, they will be good for this kind of modeling of this kind of data. Now, in that case, what happened? We'll see that instead of working with this original IT, if we take the differencing, this is a simple concept, that if we take the differencing of IT of 2 consecutive days and create a new data maybe from this IT, suppose call this new data as UT, and if you look into the autocorrelation function or correlogram of this UT, you will perhaps now see that it decays very fast. So this kind of a notion is called differencing. So this is called differencing. Now, if you see that after doing a single differencing, your data become stationary, then that means this difference data now can be modeled as an ARMA equation, okay, or can be modeled by an ARMA process. So let us see. Let erase this part. So what is the meaning of that? Suppose that this difference data is satisfying an ARMA equation. Suppose it is satisfying a very simple ARMA equation. I'll just write down. So then this ARMA equation, suppose it is satisfying this particular ARMA equation. UT is equal to okay. However, see that this is the differenced. After taking the differencing of the irregular component, you are only getting such an ARMA equation. So for the differenced series, the ARMA equation is appropriate. However, the ARMA equation is not appropriate for the original IT. So if I try to get an equation for this original IT, how would it look like? I mean, it would look like an ARMA equation, but it is not. That equation is not called an ARMA equation. That has a name that is called ARIMA equation. Why the name ARIMA? I'll talk about that.
Can I ask something?
Yeah, sure.
How did we know that the result of the differencing is suitable for ARMA?
In generally, if you take one single differencing and if you observe that your autocovariance is decaying rapidly, then that would be suitable for ARMA. If it doesn't suits an ARMA, still it is decaying very slowly, then you have to take another differencing. So that will be a second differencing or successive differencing. So you have to keep on taking such differencing. And in generally, what happens after 1, 2, or 3 differencing, you should be getting an autocovariance function which will decay very rapidly. And in that case, that differenced data can be modeled according to some ARMA process.
How do we do the second differencing, sir?
Yeah. So I just explain first. I explain this in terms of first differencing, and then I'll explain the second differencing part. So if I rewrite this UT using IT, how would it look like? I'm just rewriting the equation. UT minus 1 means this can you see that this equation IT is very similar to an ARMA equation? So if you recall the ARMA equation, it was xt is equal to phi xt minus 1 plus some phi 1 some phi 2 xt minus 2 plus theta zt minus 1 plus zt. This was an ARMA equation. This was an ARMA. So how many order of the air? 2, right? So it was ARMA 2-1 equation, right?
Yes.
Now this also looks like an ARMA 2-1 equation, but this is not called ARMA. This is called ARIMA 2-1-1. So I'll explain what is the meaning of this notation. This 2 is related to, so this 2 is related to the order of the air part, which is in this case 1. Just a minute. Sorry. So yeah. So it would be called an ARMA 1-1-1 process. So what is the meaning of that? Now in the difference data, the order of the air equation was 1, right? So I put an 1 here. That is the order of the air equation. Then in the difference data, the order of the MA part, that is 1. So I put a 1 here. And then I have taken 1 differencing. So for that 1 differencing, I put it here. So in general, the notation for ARIMA is just like for general ARMA, we write it ARMA PQ. For ARIMA, we write it ARIMA PDQ. So the P stand for the air part, Q stand for the MA part, and the D stand for the number of differencing you are taking. Just I was mentioning that in this case I have taken 1 differencing, but depending upon situation you may need to take 2 or 3 differencing. So in that case you will have an ARMA P3Q, ARIMA P3Q process. So the idea is like that. So for ARIMA processes are not same as ARMA, because the autocovariance function of ARMA has a property that it generally decays rapidly. On the other hand, if you work with an ARIMA process, recall that the UT, the difference process is ARMA, but the original process, which is the IT, that is not ARMA, that is ARIMA. So if you look into the autocovariance function of the UT, the difference process, that autocovariance function will decay very fast. On the other hand, if you look into the autocovariance of the original data or the original irregular component, the autocovariance function of the original irregular component will decay like this. So it will decay, but it will decay very slowly. So that's why this UT is an ARMA process, but this IT is not ARMA. It is an ARIMA process. Now this I stand for integrated. So this is autoregressive integrated moving average process. Now why this is called integrated? The idea is very simple. It is actually telling you that if you work with the UT, how you get back the IT? So recall that UT was defined in this manner. So that means if I want to calculate I1, I can calculate that by I0 plus U1. So from this, if I put U1, this will be I1 and this would be I0. So I1 should be I0. I can bring the I0 this side and I can write it I0 plus U1. Similarly, if I can write I2, I2 would be what? U2, I2, I1. So I2 would be plus U2. So in other words, I already got an expression for I1, that is I0 plus U1. So I can write it in this form, I0 plus U1 plus U2. So that means this IT process is obtained by adding up the U process. So it's like I start with an I0 and I add up the U process together to get this I process. So that's why this process, this addition operation, it is like integrating different component to form a whole object. So that's why this term is called the integrated. So after integrating the ARMA process, so the original ARMA process was what? The UT. UT for satisfy an ARMA equation. Now what you are doing, you are sort of adding up the UT, or you are integrating the UT to form a new process. That new process is the IT process. This IT process is no longer called ARMA. This is called autoregressive integrated moving average. So after taking integrating the ARMA process, you are getting it. So that's why it is called ARIMA. It is not called ARMA. Now, so is this part clear? Then I'll discuss something more about it. Is it clear? Is it making sense?
Yes, sir, it's okay.
Okay.
Sir, can you repeat this once?
Which one?
Just the last part.
Okay. See, the thing is that what I have told that this
এখানে
IT,
আছে
the IT has a autocovariance function like this. So it has a very slowly decaying autocovariance function. So that means our ARMA model is not suitable for it. So what I do, I'll take a single differencing of this. I'll take UT is equal to IT minus 1. And that would give me a new time series data, new kind of new time series data. And when I look into the autocovariance function of this U2, I'll see its autocovariance will be like this. So it is rapidly decaying. So that means this UT can be modeled by some ARMA process. So suppose UT can be modeled by an ARMA PQ process. Then my question is this IT is also an ARMA PQ process? No, it is not an ARMA PQ process, because if it is an ARMA PQ process, its autocovariance will also decay very quickly. But it is not decaying very quickly. It is decaying very slowly. So it cannot be an ARMA PQ process. Then my question is, what process is this then? The thing is that this IT is obtained from this line. You can see that U0 is equal to I1 minus, sorry, yeah. From there, you can see that IT, I can bring this IT minus 1 this side, and I can write it in this form, that IT minus 1 plus UT. I can write it in this form, that IT is equal to IT minus 1 plus UT. Then see that I1 is basically I0 plus U1. Thus I'm putting 1 here. I'm getting 0 here, 1 here. Then what about I2? I2 is equal to I1 plus U2, right? I'm putting 2 here. I'm putting 2 here. So I'm getting 1 here and getting 2 here, U2. But what about this I1? I have already get the value of I1. So I can input that value here to get this. So what it is telling, that you got a process UT, which is an ARMA PQ process, and then you integrate this UT process. Integrate means here adding component together to form something wholesome. So you are integrating this UT process to form this IT process. So that's why it is no longer called autoregressive moving average process of order PQ, but it is called autoregressive integrated moving average process of order PDQ, where PQ is the order of this ARMA process and D is the number of differencing you are taking. Now in this case, you are taking first differencing. In this regard, I also try to answer the question that Professor Dr. Dev has asked, that sometimes it may happen that after taking one differencing, you will see that still your autocovariance is decaying very slowly. Then what you will do? You will take the second differencing. So what the second successive differencing will give you, let me show you. So suppose Yeah,
Sir, the autocorrelation is decaying slowly or very slowly or rapidly. Sir, it is a subjective term that maybe
right, right.
slowly
This,
may for me maybe slow very slowly for you. So how can
right,
we know that? Is there any cutoff mark or something else so that we can define
right,
that it
right,
is
right. So there are actually formal statistical tests for doing that. Okay. There are formal statistical tests for doing that. However, when we use the packages, the package they themselves will carry out those procedures. There is a test called unit root test. So essentially, inherently, those tests will be applied by the packages. So
Can you please repeat the name of the test?
this is called unit root. So unit root test will tell you whether ARIMA is needed or ARMA is enough. It will tell you whether ARIMA is needed or ARMA is. If ARMA is enough, then it is all right. Okay. But on the other hand, if ARMA is not enough, we have to perhaps have to work with ARIMA process. And for that, there is a statistical test. It's called unit root test. But anyway, the package will implement it inherently. Now, let me try to answer this question that suppose I take this is actually a mathematical notation that we use for differencing. So this is called the fast differencing. Now, what would happen if fast differencing doesn't give me a stationary or rapidly decaying autocovariance function? Suppose even after taking fast differencing, you will see that your covariance function is decaying very slowly. Okay, very slowly. So then what you can do? You can take two successive differencing. So you already have taken one differencing, you apply another differencing on that. What is the meaning of that? I'm just using this mathematical symbols because this is done in this way. So what is the differencing of this? This will give me this. And what is the differencing of this? This will give me. So that means ultimately, when you take double differencing, this is also written in this way that if single differencing give you this, the double differencing will give you this. So this is the formula of double differencing. So this will be the formula of double differencing. This is the formula for single differencing, and this will be the formula for double differencing. This part is the derivation part. I just show for the sake of clarity, but this part is not really needed. The only thing is that this will be the formula for double differencing. So I think now this answered the question Dr. De has asked. So this will be the formula for second differencing. So similarly, you can also work with third differencing, fourth differencing, but in reality, it's not needed. Only second or third differencing is good enough. So people generally don't go beyond, need to go beyond that. Okay. So this will be the formula for second differencing. This is the formula for first differencing. Okay.
So
So
does
now,
the package decide? Does the
yeah,
package decide
right,
at
right,
which
right.
different?
Exactly. The package decide how many differencing you have to do, and the package also decide what would be your P and Q. So basically, the package decide what would be your D, how many differencing you have to do, what should be the lag of the air, and what should be the order of the MA. So the package determines all this PDQ. But package determines means there must be some statistical algorithm that is going on inside. Actually, there are statistical algorithm, So the package is actually implementing. Okay. Is it okay? Okay, so if I assume that this is all right for everyone.
Sir,
So
in double differencing, we have to write the order in DPQ.
in
double differencing, we have to write the order in DPQ. So say previously it was written DPQ. That's why I asked.
in double
double-
differencing, it would be basically an ARIMA P2Q. So you are taking two differencing.
Okay, sir.
So similarly, if you have to take three differencing, it would be an ARIMA P3Q. So the notation is like that. So this is about ARIMA model. There is some concept like SARIMA. So, but before knowing the SARIMA model, we should talk about little bit about the SARMA model. So what is SARMA model? So suppose this is an what type of model it is? If I ask you that this would be an what model? ARMA, right? ARMA of order what? 1,1. Now suppose you observe that your data depends on the value that you observed yesterday, as well as it depends on the not yesterday, maybe suppose this is the data observed this month, this is the previous month, and also it is what observed last year this time. So suppose this is January, this is the data for the previous month, so that means December, and this is basically last year January. So this sort of model, they are also basically nothing but an ARMA model, right? So the only part is that in a general ARMA, you have xt minus 1, xt minus 2, up to xt minus 12, but now the intermediate part is missing. Only the seasonal part. This part is actually related to seasonality. So I think you are asking that we have already removed the seasonality, then why one need to take care of this seasonality? But I then explained that there are some kind of seasonality which is not removable in that manner. So those seasonality can be incorporated with such component. So this model is actually an ARMA model, but there is a part of the ARMA which take care of that seasonality. So that's why this model has a special kind of name. They are called seasonal ARMA. And this is a seasonal ARMA. Now, while writing the seasonal ARMA, there is a technique that the ARMA part is written separately and the seasonal ARMA part is written separately. So this first part is related to the usual ARMA part. The second part is related to the seasonal ARMA part. Now for the seasonal part, you have only one component. So that's why you write it 1. And for the seasonal, are there any part for seasonal MA? No, there is no part for seasonal MA. So it should be written like this. And to show the difference that this part and this part are actually different. This part for the usual component and this is for the seasonal component. You should write the lag here. So since this is a monthly data, the lag or the period of seasonality should be 12. So that means January, then the same pattern would be repeated in the next January. So there is a lag of length 12. So that's why you should write 12 here. So this is the notation for SARMA models. Now, suppose my model is not this, but I have another additional term. Then what would happen? Now then, this is again written as the ARMA part. The usual ARMA part has one parameter, AR part one parameter, and usual MA part has one parameter. But the seasonal AR part has one parameter and the seasonal MA part also have another parameter. So in this case, it would be a SARMA model of order 1,1 and then 1,1. It is something like that. is the SARMA model clear to you? At least notationally. I mean, we don't need the mathematical properties, but the notation, how we write it and why we use such kind of a notation. Now, sometimes what happens that like we take such kind of differencing to get we take the differencing to get this difference series. Sometimes we take seasonal differencing. So that means we don't take the difference of December with the January with the December, the last month, but rather we take the differencing of January with the previous year's January. So such differencing are called seasonal difference. So it may happen that if you take one differencing, still your autocovariance function may decay rapidly, but there is a chance that your autocovariance function is decaying very rapidly. But then after a while, you see a bump, and then again it is decaying rapidly. Then after another point, you see another bump like this. So this sort of thing tells you that only taking an usual differencing like this is not going to help, but you also have to take a seasonal differencing. This sort of a differencing is called seasonal differencing. So now suppose you take one usual differencing and you take one seasonal differencing, and after that you got a process. Of course, that will be it is difficult to write that mathematically using the equation, but you will definitely get something. That something, suppose that something follows and SARMA with usual AR part P and usual MA part Q, and the seasonal AR part capital P and the seasonal MA part capital Q. So suppose this is the difference process which is following this model. Then if I ask you what is the model for the original process, definitely the original process is obtained by integrating this difference process. So it will have a process name. Now it is not called a seasonal ARMA, but it is called seasonal ARIMA. And then the notation would be, suppose you have taken one usual differencing, it will be taken of the form P1Q. And for the seasonal part, suppose you have taken two seasonal differencing, then it would be written like in this way. So in general, such models are called SARIMA, small pdq, then capital P, capital D, capital Q, and then the lag is mentioned here. The
Sir, what is
seasonal,
small d here?
the small d is the usual differencing. Suppose you have to take only one time usual differencing, but you have to take two times seasonal differencing. Then it would be P1Q, capital P, capital 2, capital Q. This small d stand for how many times usual differencing you have taken, and the capital D stand for how many times the seasonal differencing have been taken. Is it okay? I mean, at least intuitively. I'm not asking about the mathematical equations. The convention, the naming. Because when you will run software, you will see such outputs. So the naming part should be clear to you. How we are getting such process. Okay.
Or is there any simple book where we can refer back to this? Because I think we will forget this very soon.
Actually, the thing is that it is not written in a very simple-minded way. Any book, they will use lots of equations. I'll see whether I can get such handouts, maybe, which is written not in a very mathematical way, but in an intuitive manner. I'll see and I'll share with you.
Thank you so much, sir.
Okay.
Sir, can you explain the autocorrelation in SARIMA model?
Yeah.
It's
The
the figure you have.
right. So the autocorrelation in SARIMA model, how would that look like? See, for an ARMA model, the autocorrelation would rapidly decay. How would the autocorrelation of an ARIMA would look like? It would decay, but it would decay very slowly. That is the feature of an ARIMA. This is ARMA. This is ARIMA. So when you see in your irregular component, you will see your autocovariance is decaying very slowly. You should try differencing, and perhaps after differencing, it will look like this. So then an ARMA model would be appropriate. So for the original data, that means for the original data, ARMA is not appropriate, but an ARIMA model is appropriate. On the other hand,
Sir, in ARIMA model, because of differencing, the autocorrelation is decaying very rapidly, sir.
right, because
Sir,
of the
then
difference.
first one is should be ARIMA, second one is ARMA.
No. After differencing, what you are getting after differencing, you are seeing that your observed data now the correlation is decaying very rapidly. So that means your data follows an ARMA model after differencing. So I'm asking what the original data is following. The original data is following an ARIMA model, and that's why the original data, the covariance of the original data is very slowly. On the other hand, suppose in another scenario, you see your original data is itself decaying very rapidly. Then it is fine. Then you can work with the ARMA model directly for your original. But in this case, what you are seeing that your original data, the covariance is not decaying very fast. So ARMA is not appropriate. You take differencing and then you check, then you see ARMA is working well. So then you tell, okay, then my original data is following not ARMA, but ARIMA. So this is the covariance pattern of the ARIMA. Whereas in this case, your original data itself is following an ARMA. So you don't even have to do ARIMA or more complex models. Now, how would an SARIMA model look like? How would a SARIMA model look like? So let us see first I'll show you how an SARMA model look like. A SARMA model would decay rapidly. And then you'll see there are bumps in the opposite direction. Then maybe like this. Then maybe like that. So this actually indicate it is an ARMA, but it is not usual ARMA. But there is some seasonal part remains which is not removable. So that's why it will be a seasonal ARMA. And then you should use that kind of equation, the equation that I have talked about for the seasonal ARMA. On the other hand, if you are
after negative correlation, there is another decay, sir. Or there should be rise in the curve, then it will fall down.
There would be slight rise and then decay like that. And in case of SARIMA, what would happen? Your curve will decay very slowly and then perhaps go in the opposite direction. So if I erase everything, perhaps in case of SARIMA, it would look like this. Like this. So not only there is a decay, but the decay is also very slow. And there is an alternating pattern as well. So in such case, you can expect to have a SARIMA model for your data. Okay. Can I erase this part?
Yes, sir.
So that explains the ARMA model, SARMA model, ARIMA model, SARIMA model. So these are basically similar kind of model, but they have some subtle differences that we already have discussed in today's class. Now, in this case, ARMA is going to give us good results, so we don't have to go for ARIMA. Okay, because in this problem, ARMA is giving us good result. Now we talk about time series forecasting. I don't want to say much about our theoretical part of time series forecasting, but I'll be going this quickly and then I'll demonstrate. Now, once you feed this ARIMA SARIMA model, you will get the value of the parameters, and using them, you can forecast the future observation. This forecasting could be done by the software packages. Actually, they use some kind of algorithms, statistical algorithm, to do the forecast. However, they will give us the forecast for the irregular component only. But I don't want the forecast for the irregular component. So what I have to do? I have to take this forecast for the irregular component. I have to add the trend and seasonality part. Maybe either I have to add up or I have to multiply up to get the forecast for the original data. So generally this ARIMA and SARIMA based forecasting gives you very good result. But there are other kind of forecasting technique. One such forecasting technique is called simple exponential smoothing. There are certain equations for that. I'm not going to the details of those equations. But this simple exponential smoothing forecasting has a problem that if the data has trend, it doesn't give you correct forecast. So if the data has trend, then there are some variations of this simple exponential smoothing method, which is known as Holt-Winters method. However, the problem with Holt-Winters is that it can take care of the trend part, but it cannot take care of the seasonality part. So to take care of the seasonality part, there have been some modifications of Holt-Winters that have been proposed, which is called the seasonal Holt-Winters method. Now, seasonal Holt-Winters method gives a very good forecasting performance. So it is competitive to ARIMA. Now we have shown some picture. This is the difference time series, the irregular component, and then I have done some forecast for the irregular component. Now, if I want to do the forecasted value for the original time series, it would look like this. But giving forecast value may not be of much importance unless we give an interval for that, a kind of a prediction interval. So we can also give forecast interval. So this is one such example. Now I'll show two side by side. I'll show two forecast interval, one given by the SARIMA. So can you see that this is the initial air passenger data? I have shown you one data on number of airline passenger. So if you do SARIMA based forecasting, this is giving me the forecast values for the next, the number of passenger for the next 4 years. The original data was number of passenger for 12 years, and based on that, we forecast the number of passenger for next 4 years. And this is the forecast value and the forecast interval given by the SARIMA. And this is the forecast value given by the Holt-Winters, seasonal Holt-Winters. But in this case, you will see that when you are doing short-term forecasting for maybe 1 year, then Holt-Winters is giving very good forecast interval. But when you are looking into long-term, then Holt-Winters forecast interval becoming very wide. So it is becoming almost meaningless. It is not meaningful. So this is the SARIMA based forecast interval. This is the Holt-Winters based forecast interval. Okay. Okay. So now I'll demonstrate.
What is the difference between the SARIMA based forecasting and this Holt-Winters forecasting?
Okay. see, this is the SARIMA based forecast interval. You can see that in this region, the short-term forecast, this first initial period, this interval is, as you are forecasting in future, the uncertainty is becoming more. So the forecast interval widens. But if you look into the whole seasonal hold to winters, it becomes very widened. So that is the problem of seasonal hold to winters. Okay. In generally, the ARIMA based forecast interval and seasonal hold to winters give competitive performance, but in this case, at least ARIMA is giving slightly better result.
Sir, does that mean that ARIMA is good for long-term prediction and the
Right. I mean, I should not say too long term, but at least in medium term forecasting.
okay, sir.
And for short term forecasting, both ARIMA and seasonal hold to winters both perform well. You can see from the picture, both are performing almost equal.
So,
Yeah.
So a very basic question. I was seeing the forecasting trends of both ARIMA and seasonal hold winters. While the seasonal forecasting of ARIMA in the red shows three three trends which are overlapping with each other, or and
Right.
while in seasonal hold winters they take different trajectories.
Right. Those are not three trends. The middle one is the actual forecasted trend, a forecasted value. But the top and bottom part, those are actually giving you the interval, the forecast interval.
So ideally they should be closer to the trend, right, sir? Because
Yes,
in
if it is closure, that means your forecast is better. If it is too wide, like suppose if I tell you that after 1 year the number of airline passenger for this particular airline may be some number between 200 to 2000, then it is too wide. On the other hand, if I tell that after 1 year the number of airline passenger for this particular airline would be from 300 to 350, then I am giving a much more narrower forecast interval. So my forecast is then much more accurate in that sense. Is it okay?
yes.
Okay. So can you see the Jamovi screen?
Yes, sir.
Okay. So let us open the data set. I shall open this airline passenger data set. So you can see airpass.txt, that file that I have shared with all of you. Okay. Can you see the air passenger dataset in my screen?
Yes.
Have you opened the same in your computer screen also?
Yes.
Right. Okay. So this is your time series data, and you just want to do modeling and forecasting. The ultimate objective is actually doing forecasting. Modeling is not that important in this context. So
Sir,
you just
AirPass is it's like a text document. It is
right.
It's a-
.txt document. Right. You can open it.
You-
Just go
I-
there, you click it, and it should open like an Excel file. It is a simple document. It's just an
Okay.
ordinary text file. Can I assume that everyone have been able to open the file? Because I want everyone to do the hands-on
Yes, sir.
together with me. Okay, so have you already installed this Snow cluster package? If not, please go from the module and go to the Jamovi library and check available packages. And within the available packages, you will see there is a package called Snow cluster. You search SNOW and you will see immediately there is a package called Snow cluster. You just install it. Okay. So can I assume that everyone now have installed the Snow cluster in their Jamovi and it is they are able to see the icon in the panel?
Yes,
top
sir.
panel. Okay. So go to the Snow cluster. Go in the time series analysis part. You'll see univariate time series. You just click on that. You select the Y and bring it there, the variable named Y. Okay. Click the ARIMA option. Now, frequency means you want to do forecast. I want to, this is a monthly data. I want to forecast. So there will be 12 months, right? There will be 12 months. It's a monthly data. So there will be 12 months. Now suppose if it is 2, that means for 2 years for each month. So that means there will be 24 predicted value. So I put it 2 there. And then what I want to see, I want to fit an ARMA model or ARIMA model. So model coefficients. Can you see the model coefficients? It actually has fitted it. This is the AR part. So that means the AR part has order 2. And this is the MA part. This is the coefficient. This will be the phi 1 and phi 2, the coefficients related to the estimated coefficients for the phi 1, phi 2. And this is the estimated coefficient value for the theta 1, the MA part. And these are the standard error of the estimate. There is an option for getting the model fit also. So these are certain criteria in time series analysis, how we check whether our model is good fit or not. Suppose you propose one model and someone else propose another model. How do we compare? There have to be some kind of assessment that which is better model. So there are such
Sir,
model fitting criteria. Yes.
sir, what is frequency and prediction?
Yeah, frequency means if it is a monthly data, then the frequency is 12 here. Had it been a weekly data, then the frequency should be 52 because a year has 52 weeks. So in that way. And the prediction 2 means you want to predict for 2 years. So that means you want to predict the monthly data for 2 years, right? Is it okay?
Yes, sir.
Okay. Now, among these different model fit criteria, this AICC is useful in the context of time series. In usual kind of statistical modeling, you may come across the concept like AIC, BIC. These are, you may have seen this. But in time series analysis, people generally don't work with AIC, BIC. They work with AICC. This AICC means modified AIC. This is a special kind of criteria for time series data. So the less AICC is, the better model you are working with. Now, in this case, the AICC value is 1018. If it is even lesser, then that means that is even better model. Okay. Now, I
So
want
what
the
is the
prediction.
cutoff?
Yes, what is the cutoff, sir? That's what my question was.
Actually, giving cutoff is difficult in this case because for different kind of data set, the cutoff may change a lot.
Then how do we determine, sir?
Actually, you really cannot determine. I mean,
Like, sir, how did you know that 101 is appropriate?
right. Actually, I have tried out different models, and based on that, I get an idea what should be an AIC for this data.
So it should be relative to something, right, sir? For example, let's say you tried Sarima and AICC came out to be 1030, let's say.
Right.
So there should be some reference point, sir. What was that reference point?
That is what I'm telling, that kind of reference point won't work for all data set. Like for this particular data set, perhaps 1000 is a reference point. That is good enough. For another data set, maybe 2000 may be a reference point. So that's the problem.
Has to
But
be
how
some
to decide
extent.
that, sir?
Yes, sir. Yes, sir.
Right?
That's a,
So basically what you can do, you cannot decide the cutoff, but you can compare different models, consider their AICC, and take the one with the least possible AICC. But you can never say that tomorrow someone may not come up with a better model with less AICC than me. That you cannot say.
so
Okay,
basically
we have
the
to we have to build the model using different lags in
Using
AR
different
and ML.
lags,
And
different kind of ideas maybe, and based on those models, suppose you create 2-3 models or 4 models, you calculate AICC for each of the model, and then you work with the model that gives you the least AICC, because that is the model uh, that came out to be the best among the 4 you have proposed. But that doesn't give you guarantee that tomorrow someone will come up with a new model which may have an AICC less AICC compared to your model that you have proposed.
Sir,
So that's the
sir,
issue.
sir.
Yeah.
So just for clarification sake,
Right.
sir, can you please demonstrate that here in Jamovi itself, some other model other than ARIMA, where we
Yes.
calculated AICC in through some other ways?
Actually, unfortunately, Jamovi only give me option to calculate AICC for Sarima model. That's the problem. I mean, we can show, but I will try to show you that while discussing the advanced time series modeling using R. That part I'll be able to show you. But in Jamovi, they will only give you the Sarima based AICC.
No problem, sir.
Okay. Okay. Now suppose I want to get the prediction value. So I can click there. Because that is the ultimate objective, getting the predicted value. Can you see that up to 12 years data was given? So the 13th year January data is predicted here. 13th year February is predicted. 13th year March is predicted up to December. Then 14th year January, 14th year February, and up to 14th year December. Can you see that we have got the predicted value for next 2 years, each month of the next 2 years? So basically 24 predicted value for 24 months. So these are the predicted value. These are the point forecast. This is like the middle red line that you have seen in that picture. And this is the lower interval. This is like the upper interval. So you have seen 3 lines, 3 trend curves in that forecasting picture. So these are the 3 lines. This is the middle line. This is the lower line. This is the upper line. So these are basically not the forecast values. These are like the intervals. Also, you can see the picture of the forecast value. So you click in the plot part. So this will give you first I'll show you this decomposition part. This part will give you basically the trend, seasonality, and the irregular component. Can you see that? This is the original time series. This is the trend part, this is the seasonality part, and this is the irregular component. By the way, see that the software package, they themselves automatically decided that this will be a multiplicative time series. As I have told you, that whenever the periodic component is such that the amplitude of oscillation is growing with time or changing with time, then an additive model is not suitable. You should go for a multiplicative model. The software also detected the same. But of course, they have done that using some statistical procedure. Okay.
But sir,
Yeah.
just I'll be keeping it short. So let's say if we wanted to forecast the incidence of malaria cases, let's say in Delhi, sir, and we had a of number of cases in 12 months, and then we were forecasting it, sir. This forecasting will it's purely statistical. There are multiple extraneous factors which also affect that. This is there some other way, sir, in our package where we can put those extraneous factors like
Right. Yes, yes. So those will be actually come under the advanced time series model, where you use time series regression, where you have some other informations where you can put. Like in this case, I cannot put other information because this ARIMA, SARIMA, they don't allow me to put other variables. You're absolutely right. So if there are additional variables, they may be helpful in doing the forecasting, but those cannot be done in ARIMA, SARIMA models. For that, I'll be needing more advanced time series models, and that I'll demonstrate using the R package. Okay.
Thank you, sir.
Yeah. So also,
Sir, these other factors cannot be included in the irregular trends.
no, the other factor, I mean, if you don't have any information on the other factor, then they are of course included in the irregular component. But if you have information like where he's staying, what is his or her social status, then you have to include those things as a variable in your model. So that means you cannot just include them as part of irregular component. You have to include them in terms of other uh, exogenous variable or other kind of covariates.
Okay, sir.
So that's why you have to bring in a time series regression models, which are of course more advanced. Can you see the forecasted value now? So basically the same forecast you have seen in the slide, but in a red color thing. But now you can see it. This is using Jamovi. So I have forecasted for 2 years. And can you see the fitted model? Actually, it is not an ARMA model. This is an ARIMA model. And you can see that this is an ARIMA with the usual AR order 2, the usual MA order 1, and usual differencing of order 1. Then for the seasonal part, the AR usual, the seasonal AR part has order 0, the seasonal MA part has order 0, but there is a seasonal differencing that have been taken into consideration. And I have written up 12 in the suffix, if you recall that in the notation capital PDQ, then in suffix 12, they have also written that. So basically this is what is the SARIMA model. So they have written it ARIMA, but actually it is a SARIMA model. So they are using that ARIMA model to give the forecast values. So you can also get the residual plot and also get another plot for the prediction. Same plot, basically. So that means the ARIMA model, the order of the small d, the order of the capital D, small p, small q, capital P, capital Q, everything has been determined by the package automatically. Means definitely not automatic. They are using some statistical algorithm for it. But you can see it, right?
But while using R, we have to do it manually. Is it?
Aha. In R also you can do it automatically. We will see that there is a package in R that can help you to get it done automatically.
Okay, okay.
Actually, there is a package in R that do it automatically, and the same package is used by Jamovi. Actually, Jamovi use the R packages. But the only difference is that in R, you don't have the option to click and run. You have to write a few lines. In Jamovi, you just click and run and everything is automatic. So this is the better part. But the result will be exactly same. If someone runs R, the result he or she will get. And if someone runs Jamovi, they will also get same result because they are using same packages. Jamovi is also using the R package inherently. Okay.
Sir, just one question.
Yeah.
So the graph that we had for the automatic ARIMA forecasts and
Right.
the graph that we had for the prediction, are they
Yeah.
both the same?
They actually in prediction part, what they have done for the original data also they have predicted, but for the original data we are really not interested. We are interested in the prediction in the future part, but that part is exactly same. That part is exactly same.
Okay, sir.
So here prediction means they have also predicted for the data value, which is not useful for our purpose, but that has some other use. So they have done prediction. But this blue part, which gives you the prediction for the future, and this blue part, which gives you the forecast for the future, the prediction and these two things are exactly identical. There is no difference.
Okay, sir.
Okay.
Sir.
Yeah.
Like in this model, you have taken like past 12 years data, right? So
right.
What would be an ideal like or minimum interval of data which we need to consider for conducting this type of analysis? Like, will the past 5-year data will be sufficient enough?
Yeah. But that also depends on what type of data set you are considering. If it is too complicated, like it is relatively showing simpler pattern, like there is an increasing pattern and it is the number of passenger is increasing in a consistent manner, and also there is a periodic behavior, and that periodicity also increasing in a regular fashion. But suppose your data, when you do the time plot, it looks very complicated, very weird kind of shape. So in that case, may not be only 4-5 years may not be sufficient. You may have to have more number of years. But for usual kind of time series data, 4-5 years is good enough.
Okay. Okay.
For very short term forecasting, of course, you cannot forecast even medium term if you have less number of data. So 5 years data means if you have if you are working with monthly data, you have 60 data points. So with that, you cannot forecast too much. Maybe focus for a few months ahead.
So, sir, taking from sir's question, the historic data should be minimum of for 50 months to forecast for next 1 year only, right, sir? Ideally.
For
Sir, so taking from what sir said, the data point, the historic data should be only 50 months data should be available with us to forecast for next 1 year or next 12 months.
Yeah. But definitely
So,
not more than that. If you try to forecast more than that, you will see that your forecast interval will be wide, and that means your forecast doesn't has much reliability. So whatever you are saying, it doesn't have much reliability. It's not useful then.
okay, sir. Like in this, sir, and the airline passengers, let's say, for example, we are forecasting for one particular company, and
Yeah.
we had a historic data of, let's say,
12
5 years,
years.
sir.
12 years. Okay.
Sorry,
For
sir.
you are assuming 5 years. Okay. Yeah.
Okay, sir. And and then, sir, COVID happened, and then the business completely flopped. And then again, we forecast like here it is this event, major event, sir. Will this will impact the trajectory of forecasting also, sir?
No. It won't work in that case, because there is a sudden change in the system. So you have a data from the previous state of the system. Now the system got completely changed, and now you try to forecast based on the previous data. It is not going to give you same result. Not going to give you good result. It is only applicable when your system remains in the similar state. Okay.
Sir, one question.
Yeah.
Sir, it is predict only the for the next 2 years, sir. Sir,
Yeah.
can it be Sarima Holt Winters model, sir? And Holt Winters forecast? Because it is
Can it be?
Sir, Sarima Holt Winters forecast because it only predicts the only 2 years data.
No, that you can easily change. Suppose I am inserting in place of 2, I am inserting 10. Then it will give me 10 years forecast. You can check. It will give me 10 years forecast. So that's not a problem. So can you see that it is now giving 10 years forecast?
Yes, sir.
And Holt Winters is a different forecasting algorithm. It has nothing to do with Sarima. Sarima is very good. Like if you want to do short to medium time forecasting, Sarima model is very good. That's why the focal theme of our time series workshop was Sarima modeling. Okay, because it works very well. And it has a very well established principle how to proceed with Sarima model. We have also seen that. But Holt Winters is another approach. Holt Winters is also another approach, but Holt Winters is essentially used for only for forecasting purpose. Like Sarima, we created model, we estimated parameters, so those part was also of interest to us. But in Holt Winters, only forecasting is highlighted. That is the main objective. Holt Winters is a forecasting algorithm. It's not a model like Sarima.
Okay, sir.
Now, there is also another type of forecasting algorithm which is available, but I'm not going to show this today. Maybe we can discuss that in the next class. So that is called Prophet analysis. So we'll see that later. Okay. So I think it is better that if we stop here today and continue this thing in the next class.
Thank you, sir.
Okay. So maybe we can end the meeting for today then. If you don't have any more question.